In this presentation, I will summarize the core findings of our research project titled Sustainable Architecture Decisions in the Cloud, Reconciling Performance, Cost, and Environmental Impact. Our research is motivated by the rapid expansion of cloud-based systems and the increasing recognition that software sustainability is no longer optional. Cloud adoption introduces complex trade-offs among environmental impact, cost, performance, maintainability, and long-term system evolution. Yet the research landscape remains fragmented and lacks cohesive frameworks that address sustainability in its full multidimensional form. This leads to my central research question. How can sustainability be systematically embedded into software architecture and evolving large-scale cloud systems while balancing cost and performance through standardized empirical evaluation? To explore this question, we synthesized findings from 7 representative studies across cloud architecture, agile development, carbon-efficient design, architectural knowledge practices, software quality measurement, practitioner perspectives, and macro-level environmental analysis. From this synthesis, 3 major themes emerged. First, sustainability is consistently treated as a multidimensional construct spanning environmental, economic, technical, and social dimensions. However, most existing research predominantly addresses environmental and economic factors, while the technical and social dimensions are significantly underrepresented. Second, all 7 studies highlight major challenges in measuring and operationalizing sustainability. Across the literature, there's a lack of standardized metrics, limited empirical validation, and insufficient long-term or reproducible studies, particularly in carbon-efficient design and cloud architecture. As a result, sustainability remains difficult to embed in engineering processes in a systematic and measurable way. Third, there is a clear gap between academic models and practitioner perspectives. Practitioners consistently prioritize cost predictability, deployability, agility, and operational continuity. These priorities do not align cleanly with academic sustainability frameworks, which tend to emphasize conceptual multidimensional balance rather than the constraints of real-world cloud environments. This mismatch makes practical adoption of sustainability techniques difficult. Turning to the synthesis matrix, several important takeaways emerged. Across architectural studies, sustainability-oriented solutions in cloud systems are highly uneven. Most architectural approaches focus on optimizing cost or energy consumption. Very few address all 4 sustainability dimensions simultaneously, and almost none provide empirically validated evidence for their effectiveness. Research on sustainable quality in use shows that even widely used international standards lack the ability to measure long-term context evolution, risk, or sustained usability. Similarly, systematic reviews on carbon-efficient design reveal the absence of validated metrics and a heavy reliance on conceptual frameworks rather than operational tools. Practitioner-focused research reinforces this pattern. In real-world engineering discussions, environmental sustainability receives very little explicit attention. Instead, practitioners repeatedly focus on cost-effectiveness, scalability, automation, maintainability, and vendor constraints, dimensions that academic sustainability models often overlook. Finally, macro-level environmental analyses show that cloud adoption does not automatically reduce emissions. Instead, environmental impacts depend heavily on sector characteristics, national energy infrastructures, and long-term policy environments, indicating that sustainability must be understood as a system-level property rather than a local architectural decision. In conclusion, the literature collectively demonstrates that the field of sustainable software engineering remains conceptually rich but practically underdeveloped. To systematically embed sustainability into cloud architecture, the field must move toward integrated frameworks, standardized and validated metrics, and greater alignment with practitioner needs and constraints. Only through these advancements can sustainability evolve from a theoretical ideal into a measurable, operationalized, and consistently applied architectural principle. Thank you,